Good afternoon. Welcome to EE222. We were looking at different ways of representing circuits, right? And so far, let's do a quick review. In the beginning, we learned about I think we learned a few things in parallel. One way to represent a system. The system may be the combination code to a bank vault, or the system may be some security system, or the system to turn on and off the cooling system, cooling air conditioner for your lecture room or for your bedroom, right? Or vending machine. That's another possible project which you guys could take up after doing this particular course. Because it counts coins and there's discrete numbers. So one way to do draw up or describe a system is by drawing the truth table. You put all the possible inputs, you find what are the possible outputs, add those possible combinations. So the problem with truth table, what is the problem with truth table? Truth table is, okay, it's okay. If you have 2 inputs, you have only 4 possible combinations, 4 lines. 3 inputs, 8 possible combinations. 4 inputs, how many lines? 16 lines. It starts to become very cumbersome. If you have 5 inputs, you have 32 possible combinations. So if you're doing, let's say, a vending machine problem, right? I'm just saying hypothetically. So how many coins do you have? You have a 5-cent coin, 10-cent coin, 20-cent coin, 50-cent coin, $1 coin, $2 coin. 6 possible combinations, 6 possible inputs. So 2 to the power of 6 is 64. So your truth table becomes very long, 64 lines. This becomes very hard to handle. Even though the concept of a truth table is very easy. The concept of the truth table is very easy to handle. But once you start to get very lots of inputs, it becomes very long. Okay, let's look at another problem. Another way to describe a system is, instead of truth table, we can just draw the circuit. Nice, you can draw the circuit. But once again, if your system is complex, your circuit can become very, very large. Right? Okay? It can become very, very large. Right? And especially if, let's say, the supplier says there is no such thing as a 7-input or 6-input AND gate. Then you have to build a system which will build a 6-input AND gate for you. Yeah? Okay. Then, okay, so circuit, drawing a circuit is good, very diagrammatic. It gives you actual information of how you will be implementing it in hardware, but it's very hard to look at, right? Now, the next line. What's the next line? The next one is timing diagram. Timing diagram, once again, few inputs, it's okay. If you get many inputs, you have to take it for a very long number of combinations. So timing diagram, if you have 2 inputs, you have to make 4 iterations. Not only do you have to have 4 lines, sorry, you only need 2 lines if you have 2 inputs, or 3 lines. 2 for the input, 1 for the output, but you have to make 4 iterations, so it goes lengthwise, okay, it goes longer, right? And if you have 16 inputs, you have to go 16 iterations deep. All right, so timing diagram, again, very cumbersome. It's similar information to truth table, by the way, only shown in a diagrammatic way. Okay, so we have another way. Another way is to write the sum, another way is to write the Boolean expression. Boolean expression is good, but once again, you may have to do some minimization. You don't know the number of layers, how many layers. We learned this yesterday, right? But it's probably one of the best. It's like what I'm showing you over here is one of, what would be the best possible combination to do a particular or describe a system. Then you have sum of products described in Boolean algebra. Sum of products in Boolean algebra, fine. Can become very long if you have a large number of inputs. So if you have 4 4 inputs, you will end up with how many minterms? I want you to recall over here. How many minterms will you end up with? In a sum of products, see, sum of products can be described in 2 ways. Sum of products can be written in 2 ways. Firstly, it can be written in an algebraic form, algebraically, right? Let me just log in over here and show you what algebraically means. Okay, we were on okay, let's have a look at this. We've done all of this. Right, all of that has been done. Okay, so sum of products, guys, sum of products can be described in 2 ways. There's 2 ways to write it out. One way is to write it out algebraically, like that. Okay? Okay, like this, in Boolean algebra format. Another way to write a sum of products is in this form. Let me show you. This form. How can I do marquee zoom over here? I can't. There we are. This is another way to write it. This is called the sum of minterm expression. I did this yesterday, right? So this is a recap. This is called a sum of minterm expression. I mean this line here. So this is, both of them are sum of products. I repeat, both of them are sum of products. All right? One is written in the algebraic method, sum of the algebraic expression of the sum of product expression, and one is written as the sum of minterm expression. Now, obviously, you know this symbol stands for sum. This lowercase m stands for minterm, lowercase. Don't play around with the cases over here, all right? Just like in Boolean algebra, you can't play around and assume plus is, you know, addition and all that sort of thing. No, they mean particular things, all right? Don't do a prime. Prime means, what does prime mean? Invert, right, or not, right? And over here, these numbers are the addresses of the locations of what? The ones. Now, my trick question to you. If you are given, in this system, how many inputs were there in this particular system? There were 3 inputs, right? How do we know? Well, sometimes we write it out as Z, open bracket, A, comma, B, comma, C, indicating that this was a system of A, B, and C inputs, right? And the output is Z. Okay, now, tell me if, let's assume that we had Z of A, B, C, D, E, right? How many, what do you call one of these guys? That's a minterm. What is it built using in hardware? Think about hardware. Minterm refers to AND gate, right? And what are they all those AND gates feeding into? An OR gate, all right? So how many layers over here? How many layers? 2 layers. 2 levels. 2 levels or 2 layers? 2 levels. All right. Now the first question. If this was a 5 input system, you can note this down if you want. If this was a 5 input system, how many levels? How would this be affected in terms of the number of levels? The number of levels, how would it be affected? How many levels would there be now if it was a 5 input system, A, B, C, D, E? Okay, let's put your hands up. How many people say there will be now 5 levels? 5 levels. Anyone saying 5? How many saying there will be now 4 levels or 4 layers? How many people say 3? Go on, it's not going to cost you any marks. 3? What do you think? 2? Right? How many people say 2? How many people say it's going to go down to 1? Okay, 2. So that's good. You guys got it. Right? It will remain 2. That's the thing about sum of products. No matter how many inputs you place, the number of levels or the number of layers remains the same. And if it's sum of products, the first level will always be, what will the first level always be built with? Just AND gates, and the second level will always be OR gates. How many OR gates? 1, right? But sometimes, in reality, let's say if you had 7 AND gates, there's no such thing as a 7 input AND gate. If you want, even if you want to go and buy it from any electronic store, whether it's in Fiji or it's in China or Taiwan, you won't be able to find a 7 input OR gate. You will not be able to find a 7 input OR gate. So in that case, you have to build a 7 input OR gate. All right. So that's another reality of what's happening on the ground. All right. Now, next question, so that you have an understanding. Yeah. Sorry? Yeah, if you let's say there were 7 minterms here. Let us just assume there were 7 minterms, right? So the first layer is easy. It's all AND gates, individual AND gates, right? The second layer, you need 1 OR gate, right? But that OR gate would need 7 inputs. But in reality is, when you, in the diagram you will show 7 input, but in implementation on your hardware, there's no such thing as a 7 input OR gate, right? So you have to build one. How do you build a 7 input OR gate? Yeah, you have to put daisy chain, what they call daisy chain, a lot of OR gates together. Yeah? Okay. I'll show you that in a short while. I'll show you that in a short while. All right. Now, yeah, you understand what daisy chain is? Yeah. I'll show you the implementation later on. You guys might understand this. Sometimes your laptop has got only 1 USB output. Yeah? You get a USB extension, which has got 4. You plug that 1 into this, and then you plug 4 into that. Yeah. Something along those lines. That concept, but not exactly that, but that particular concept. That's called daisy chaining. All right? Okay. All right. Now, okay, my next question is this. You have a 5 input system. How many minterms will you have? Okay, I'll give you 1 minute to talk with your neighbor or with your friend or your imaginary girlfriend. You have a 5 input system. How many minterms will you have? You may want to refer to what we did yesterday, if you wrote it down in your book. You know, I did it on the board on the Microsoft Word. I typed it out, but if you want, you can, Okay, another 10 seconds. Anybody got an idea? Anybody got an idea? 5 inputs. Yeah, okay, go ahead. You can take a guess. It's not no big deal. Yeah. 16? All right. Okay. Anybody looked at yesterday's notes or anything? Anybody? 16? 5 inputs. Some people saying 16 possible midterms. Remember, this is one midterm. This is one midterm. So they're saying there will be 16 AND gates. Yeah, 16 AND gates. Yeah, midterm. That's so if you didn't understand what midterm means, one of those terms is one midterm is one AND gate. All right? Anybody else? Another one. Another 2 people before I give you the answer. Unless somebody answers it first correctly. Anybody? He's saying 3? 3 midterms. Okay, another guy is saying 3. Anybody else? Anybody else? 5. Saying 5. Okay, now, what is the procedure? Now, I'll ask you this question here. What is the procedure in order to write the sum of products expression? What is the procedure? What is the procedure? Can somebody tell me from yesterday? I gave you steps. Step 1, do this. Huh? Identify the ones. So the answer to the question was, there will be as many minterms, the number of minterms is equal to the number of ones in your output column. So there's no fixed answer. Yeah? Yeah, okay? All right. Okay? The number of ones, wherever there is a 1, there is a minterm. All right? Okay, now, everything I just taught you, everything I've just taught you for sum of products, the same is true for product of sums. Right? What is this the location of? This is the address of all the zeros. And in the first layer, what do we have? We have OR gates. This here in the brackets is called a max term. And all these OR gates are what? They are feeding into what? The second layer, the second level is one AND gate, a singular AND gate. All right? Okay? And this is, and how do we, what is the procedure for identifying, what is the steps you have to follow? You have to identify all the zeros. So you don't know what the system behavior is. The system behavior is based on whatever the designer made it to be. Okay, so let's do a real problem. Let's make let's make a let us call this an odd number detector. Okay, let me flip over and then we'll. Okay, so we're on week 5, lecture 3. Okay, no, not odd number. Let's call this a majority detector. Majority detector. We're doing an example on a majority 1 detector. There are 4 inputs. And let's be fast now, all right? C, D, and output F. What I can say over here, guys, is that our system can be written as F of A. Look at the notation. B, C, D. That is how our system is written. F, it's a function of A, B, C, and D, which means there are 4 inputs. Now, obviously, by looking at this, right, and this system is a majority 1 detector. So we can draw our truth table. We can draw the skeleton of our truth table. 0, 0, 0, 0, 0, 0, 0, 1. So guys, how many possible combinations will there be? 4 inputs, so how many possible combinations in the truth table? 2 to the power of 4 is 16. All right. 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. Now, this is another quick way of doing it. There's always a pattern. Okay, so the input side of my truth table is now populated. Set the input side of my truth table is populated. Fairly easy, because you just see the combination, you write it out. Yeah? You shouldn't need to, by the way, you shouldn't need to look at my screen in order to fill the input side. You should be able to fill it out yourself because you know the combination. It's natural binary, all the possible combinations for 4 inputs. Right? Now, what do we call this? Let's call this line 0, line 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. Why did we stop at 15? Earlier on, we said there was going to be 16 possible combinations. Why did it stop at 15? Because we start from 0. So these lines over here are the address numbers. The address. Remember that word. It's called address. Okay? The line address. Okay, now, it's a 1 majority. So the output will only be 1. The output shall only be 1 if 1 is in majority. If and only if 1 is in majority. Okay? All right, so first line. Are there any 1s? No. So output is 0. Second, line 1. There's only 1, 1, but the zeros are in majority. So 0. Line 2, 0 is in majority. Line 3, 2 1s and 2 zeros. No, we want an absolute majority. Right? So maybe you want to note it down that draw the truth table of a system where, of a majority system where 1s are in absolute majority. Write down greater than 2. There must be greater than 2 1s. Right? Absolute majority. You can't have 2 and 2 equal. Set? Okay? So in this case it was equal, so we give it a 0. This one, line 4, 0. Line 5, 0. Line 6, 0. Line 7, 1, because 3 against 1. Line 8, 0. Line 9, 0. Line 10, line 11, 1. Line 12, line 13, 1. Line 14, 1. Line 15, 1. Right? Absolute majority system, not just majority, absolute. Because if you have even numbers, there's no way, you always got something there, right? Okay, you always got a draw, 2 and 2. Okay, now, now, I want you to now, let's describe the system as a sum of products in algebraic manner. So what we do is, for sum of products, what do we have to identify, guys? All the 1s. So let's have a look at this 1. How can we write this line over here? Line 7. There'll be, what will be that written as? There'll be A bar and B and C and D. What about this line here? A and B bar and C and D. There'll be A and B and C bar and D. This will be A and B and C and D bar. And this will be A and B and C and D. All right? Okay. So the sum of products expression in algebraic form will be written, the algebraic form will be written as f of a, b, c, d is equal to, put all those terms together, a bar, b, c, d, or a, b bar, c, d, or a, b, c bar, d, a, b, c, d bar, a, b, c, d. 1, 2, 3, 4, 5. There we go. Okay? Do you see how I did that? You identify the ones. All right. Now, let's now, as second question, I want to rewrite that as the sum of min-term expressions. So I did this yesterday, and this is also on Moodle, but this is a new problem altogether. I just made this now. All right? Okay, now, let's now write this in SOP. I want to do an SOP, but as the sum of min-term expression. So we say f of a, b, c, d is equals to sum lowercase m, open bracket. Now give me the addresses of the places where 1 occurs. So it will be 7, 11, 13, 14, 15. There we go. 7, 11, 13, 14, 15. That's all it is. So when you look at the sum of min-term expression, that's a very easy way to describe a very large function. Even if you had a system with, let's say, 30 inputs, you'd be easily able to write it out. But if you had something like this, your expression can become very long. Now, let me write out, just for some lines, the product of sums expression. Now, for product of sum expression, all right, guys, sorry. Another step over here. So number 1 was this, the algebraic. Number 2 was rewriting that. This is just different notation. Both of these systems are both sum of products, except for different notation, right? Just the notation has changed. Okay, now, there is another way to describe this circuit. What do we need to do? We need to do the AND/OR circuit. Okay, so you do that as part of your homework, okay? The AND/OR circuit. Obviously, how many levels is it going to have? 2 levels, right? And by now, you've picked up how many AND gates? How many AND gates, guys? 5 AND gates and 1 OR gate, right? Okay, now, let's now have a look at the product of sums. The product of sums. So let's flip back to the truth table. The step is, what do we identify when we're dealing with product of sums? You have to look at the zeros, all right? So let's have a look at this line. Now, I won't do all of them. There's quite a bit over there. I'll do the first 4 for you. So we will write that out as, A or B or C or D. When you OR A or B or C or D, you still get a 0, right? Because the target is you want to get a 0, right? So A or B or C or D bar. A or B or C bar or D. Let's do the line 3. A or B or C bar or D bar. Line 4, A or B bar or C or D, Right? You guys get the picture now. And then obviously you do homework for all of that, okay? You guys got to fill out, I'm not going to write everything out, guys, so you have to fill out, okay? Now, another way of writing this is, so how are we going to write that out? Let's look at line 0. What was line 0? A or B or C or D. And then what's line 1? A, B, C, D bar. A, B, C, D bar. Okay. What's line 3? A, B, C bar, D. A, B, C bar, D. Line 4. A, B, C bar, D bar. A, B bar, C, D. And the list continues. Okay? Can you see how we've put all the brackets together? Yeah? Okay? Obviously, you've got to fill that up, finish it off with your homework. Right? You've got to do homework over here. Okay. Let's look at the product of sums, but I want it in the product of max terms expression. Right? And the way we write it out is like this. It's f of A, B, C, D. Look at this notation. It's not pi. Okay, it's the gate signal. Okay? Gamma or gate signal function. Capital M, uppercase M, not lowercase anymore. Open bracket, and what do we put inside those brackets? Right? The addresses of all the zeros. So can you give me the addresses of all the zeros, guys? 0, 1, 2, 3, 4, 5, 6, 8, 9, 10, 12. That's it. Okay. So the catch over here is, when you look at the product of max terms, that number cannot be occurring in the sum of min terms. 7, 11, 13, 14, 15 cannot be showing over here. Yeah, obviously you're either a max term or you're a min term. Okay? They can't be both. Well, there's actually something for both as well. Right? It's called a don't care, and I'll explain that to you guys later. So obviously, as part of your thing, you've got to do something known as an or and circuit. Right? And that's fairly easy. The circuits are fairly easy. Right? Now, then we come to one last stage. Before we finish off today. So we've done all of these, guys. Yeah, you have a look over here at Boolean algebra. Right? So sometimes, okay, the catch over here, guys, the catch over here is that obviously, this function, is it minimized? No. It is not minimized in terms of number of gates. It is only, what is the purpose of product of sums and sum of products? What is our objective when we go into that line of thinking? We want to control the number of levels. We want to standardize the number of levels, right? Very clear number of levels, because that helps us in doing coding. You know, when you want to code a particular chip and that sort of thing. So that helps you in that. But it is not minimized. That's the catch. It is not minimized, but it's easier for coding and manufacturing. All right? Okay. Now, but it's not minimized. So what I show you over here is, what they've gone and done is, he's gone, in this example, they've minimized. They've written the sum of products expression, And then they've attempted to minimize it using our Boolean algebra and so forth. All right? So you start off with sum of products and you end up with Boolean. But they both mean the same thing. They will both, whether you're over here or over here, you will always get the same output. It's the same system, just written in different ways. With minimization, you get reduction, all those things which I spoke to you about yesterday. The 10 reasons why we do it. All right? Or was it the other day? Okay? Now, all right, let's now move down further. Okay, Boolean simplification, you guys are all familiar with that now. We've done a lot of good problems on those. Okay, now I introduce you to another concept. So look at this. This is and/or logic. Sometimes they call it, I use the word circuit, and/or circuit. Sometimes you might be asked to draw the and/or logic. It means the same thing. And/or logic and and/or circuits means the same thing. All right? All right, now, this is the catch. So the last step is to bring it into a NAND realization. NAND realization, right? Or a no realization, right? So and or, okay, fine, you're using two different types of gates. But in NAND, you're only buying one type of gate, right? So you just go to one manufacturer and you just place an order, say, I only want NAND gates, right? What would be easier? Let us just give you an example. What is easier, to build something which has many parts? Let's bring it in terms of food. What is easier, to cook something like chicken chop suey, which has got multiple ingredients? You've got a couple of vegetables, you've got your chicken, you've got a couple of different sauces, salts, spices, so forth, right? Or is it easier to just do something like potato and roti, two ingredients, yeah? Or fish and chips. Fish and chips is a better example. Fish and chips, two ingredients. Always easier for the manufacturer. It's easier to go with something which has got fewer ingredients. You can control, you can move faster, right? If you're doing something which has got many ingredients, even if one part falls apart, one supplier breaks down. So let's say you are depending on, let's just say you are a factory which produces chicken chop suey, which provides food for the whole university. One day, the chicken supplier called up and said, sorry, no chicken, boss. What happens? You see what I'm saying? Or somebody said, oh, sorry, no rice. We ran out of rice. Right? Okay? Yeah? All right? You see what I'm saying? There's a total breakdown. So it's always easier for the manufacturer to design your circuit with minimal number of, that's another design philosophy. Right? Sometimes one philosophy is to reduce the circuit as much as possible. Another way to design it is design it, but just use one type of gate. Don't use anything else. Make it all easy. All right? So there we go. So this is a NAND realization. A NAND realization. How did they do NAND realization? How do you go from, oh, the problem is given here. How do you go from there to this? Anyone got an idea? All right? De Morgan's theorem. It's called De Morgan's theorem. You guys know this. I think it's theorem number, what is it, 13? Right? That's going to be your lucky number. All right? Okay? De Morgan's theorem. So note that down. I want you to attempt this problem and apply De Morgan's theorem to get the NAND realization. What are we going to do? I just did this the other day. You put a double bar on top. You put a double bar on top, break the lower bar. All right? Okay? Break the lower bar and then you can change the sign. Okay? Attempt this. Maybe just jot down some notes. You put a double bar on top. I did this in one of the problems. We were converting all the gates to NAND, building everything with NAND. Yeah? And universal gates. That was the name of the topic. Right? I think it was on Monday or Tuesday. Right? Yeah. So, NAND realization. And what do you use? You use De Morgan's theorem. You put a double bar on top, you break the lower bar. Okay, all right. So if you've missed out on Tuesday and Wednesday's lecture, you'll start to feel, right? And again, if you have NAND, okay, this is OR AND logic. You can convert that to no as well. Same concept applies. NAND, no, same thing, right? All using De Morgan's. Remember, De Morgan's, if you look at theorem 13, right? If you look at theorem 13, there were two versions, right? One is the NAND version and one is the no version, right? So this is where now our course EE222 is now changing. Until now, we were doing basic things, divide by 2, find the remainder, learn how to count, all these sorts of things. Now we are applying knowledge which we learned within the course. You are now moving away from secondary school and primary school. You know, we were doing associative law, commutative law, all those things. I was looking at the students, they were smiling. They said, oh, okay, this is easy, right? Okay, now we are actually applying our own knowledge, De Morgan's theorem, which you just learned in theorem 13. So you've got to learn how to apply it now. And as we move on, we will continually use what we learned in week 4, week 5, week 3 to build, right? So we're building on previous knowledge. So my point is this: if you haven't been doing your revision, if you haven't been studying, things are now going to move very fast. Okay? So look at this. This was another one. Okay, so this is realization into no. There we go. This is no. So let me just flip over to the document camera. What time is it? All right. Okay, so we have to do NAND. Okay, sometimes people call this logic. Okay, that's part of homework. And this is no. And that's part of homework, right? Guys, if I give you homework, that means there's a high likelihood that I will give you a test along those same lines, all right? So make sure whatever I give you, you try and study in your free time. Okay, we're in university now. It's not a spoon-feeding environment, right? You have to do independent study in order to get along. Let's just see quickly, guys, if you've written that down. That's it for the writing part of today. I'll just show you some other things. Okay, let's go. Okay, we've done this. So this one here, week 3 one is done. Week 4, all right. Okay, this is the problem which I was talking about, daisy chaining and so forth, right? So week 4, this is some basic stuff. So if you have a 3-input or a 3-input OR gate, and you want to convert it to a 2-input system. So one way of doing it is like this. Well, let me zoom in over there. Okay, so that's a 3-input AND gate, and this is a 3-input AND gate, and you want to convert it. And you say, let's say you go to the technician and you say, hey, or a shop, and you say, in my design, I need a 3-input AND gate. And the shopkeeper says, sorry, no, we don't have 3-input. Sorry, you need a 2-input AND gate. And the shopkeeper says, sorry, you don't have 2-input, we've got 3. So you should know the technique of converting, right? How you convert 3-input into 2-input. So you just place a 1 there, right? Something similar to what we did earlier on. Remember, with what principle is being applied here? Which theorem? Try and figure out the theorem, right? Just for homework, just note it down. What theorem is being applied here? It's one of the theorems. Everything ends up with one of the theorems. Application. In the theorem, when we wrote it down, we looked at it from a mathematical point of view. But I always asked you to leave some space and draw the equivalent circuit, because there is a theorem. That's an identity. The one over there is an identity. Okay? Now, over here, OR gate, the 0 is an identity, right? 0 is an identity for the OR gate. So this is how we convert 3 to 2, right? Downsize, 3 to 2, all right? Okay? 3-input NAND gate using 2-input NAND gate. There we go. All right. So this is all on the Moodle shell, guys. This is all on the Moodle shell. So I don't want to go around and draw everything. So this is another one where we are sharing gates, and basically we are reducing the number of gates. Right. So there's a function given. So this example is already done for you, and I want you to just take note and make sure you attempt and go through this problem. Right. Make sure you go through this problem in your free time. Right. Another one. Let me give you another one. Okay, don't worry so much about full. You can have a look at full adder. NAND gate. So basically the concept over here is, you've been given a circuit. Sometimes the word may become scary. What I mean is you may feel, oh, I haven't done a full adder yet. Right? But the question is basically saying, this is what the question is asking you. The question is saying, can you redraw that circuit in NAND logic? So convert everything into NAND. And we've done that. Now, let me start with this. Can we convert this into NAND? Yes, it's already in NAND, so we don't need to do any conversion. This one, done. This one, done. What about XOR? Do you remember I said, hey, XOR is what? Is equals to A bar and B, or A and B bar. So then for each of those, A bar and B, A bar you can do using NAND. And B, the N you can build using NAND, right? B bar you can do using NAND. From B you put, you tie the NAND inputs of the NAND gate together. N you can again do using NAND. So you can build an XOR. I think it was one of the homeworks, yeah? One of the homework was to build XOR gate using NAND gate. So make sure you revise check your own homework, all right? And then that's how you connect it together. So that's what that's what the question is saying. Redraw the circuit in NAND logic. Right? There we go. Everything in NAND. Everything in NAND. Okay? And then I said, hey, oh yeah, this is what I did. I said, firstly, draw the NAND version of, draw the NAND or universal gate version of XOR. Then I said, hey, this is another one with only 4 chips. And I said, compare. Yeah, that was there in the homework. Let's see, somewhere around, yeah, it was just the other day. When was it? Build homework. Says homework. Build XOR using NAND. Use the formula given at the start of week 5, lecture 1. Right? Okay? So there we go. And then I said, okay, this is an alternative circuit. This is an alternative circuit for XOR using NAND. Alternative to this guy. All right? And I said, okay, do all this and, okay? All right. So,